Good morning, class. Today we'll be talking about angular momentum. As always, we'll have a brief review of what we did last time, and last class really nicely connects to the discussion of this class. So last time we talked about quantum mechanics in 3 dimensions, and we introduced the idea of the Schrödinger equation in different coordinate systems. Cartesian and a circle are the ones that we looked at. So let's consider the Schrödinger equation in a 3-dimensional form. This is the momentum piece. And then the potential. And we can do separation in variables in Cartesian coordinates or spherical coordinates depending on the problem to attempt to solve the differential equation. We looked at the case for the potential being equal to 0. You can consider, that's just the 3-particle case, you can consider parabolic potential. You can also consider an infinite square wall case. And I think we introduced last time also the idea of this Coulomb potential. 1 over r, where r is a square root of x squared plus y squared plus z squared. And we noted that separation of variables is impossible for this case. But we noted that this works in spherical coordinates. So what we did is we translated and transformed the Schrödinger equation into the case for a spherical coordinate system. And we decomposed it into radial momentum and an angular momentum piece, P sub r and L. And now we're dealing with a case where we have the potential as a function of r. So it has this spherical symmetry. And we defined or found that we can decompose the wave function into a radial component and an angular component, r and y, where this y are known as the spherical harmonics. And if we plug this solution back into the Schrödinger equation for spherical symmetry, we will get the following. Let's call this equation number 1. This is dependent on just the radial component eigenfunctions. We have a second equation depending on the angular components, theta and phi. That goes like this. This is the second equation. So we've separated the Schrödinger equation into 2 bits, one that's dependent on r, one that's dependent on theta, and phi. What we can do next is separate this even further, the 2 variables here. We can separate this into theta and phi. We did that last time. We can make this separation of variables capital theta, and y is equal to capital theta times capital phi. If we solve this, plug this back into the Schrödinger equation, for the angular piece, it will yield the following. Let's call this equation number 3. Notice that here we have only the differential equation varying in the functions of theta, and phi has disappeared, and it reappears in a separate equation. And we talked about the eigenfunctions being this EVIM T expression. Okay, so this is all kind of a review, and the last thing in the review is that we found a few of these expressions for the Legendre polynomials, these capital thetas. And examples we found for n equals 0. We find the Legendre polynomial being constant. For n equals 1. The Legendre polynomial goes like cosine theta. And L equals 2. It goes like a half. 3 cosine squared theta minus 1. Okay, and that's all. Alright, so that's a review from last time. And so let's segue into talking more about angular momentum explicitly, though we know it pops up here and here for spherical harmonics. So let's delve a little bit deeper and talk about more about angular momentum. This L here. Okay. Let's take a step back and think about the classical definition for the angular momentum. Remember from your mechanics class that angular momentum L is equal to R, radial vector, times P, momentum vector. And we can calculate it by calculating the determinant of the matrix, where the matrix is looking like this. This is equal to the following: I pz minus z py in the I hat direction plus z px minus x pz in the j hat direction plus x py minus y px in the k hat direction And it turned out that this part is L sub x, and this part is L sub y, and this part is L sub z. And so we typically write angular momentum in terms of its x, y components like this. Lx, Ly, and Lz. Now let's take a break and do the first in-class assignment for the day. And when you return from that, we'll continue. First, I'd like you to recall that p sub x is h bar over I ddx. That's just the definition for that linear momentum operator. And so if the linear momentum operator has some expression that is derivative, we might want to ask what is the angular momentum operator expressed in the spherical coordinate system, or how is it expressed in the spherical coordinate system? And that's what we'll try to answer next. In order to do that, let's do a change of variables. So let's consider Lx, Ly, and Lz in the spherical coordinates. And to do that, we need to change the variables, and the variables will change. Rx is equal to r sine theta cosine phi. Y is r sine theta sine phi, and z is r cosine theta. Okay? And essentially you get these from looking at the coordinate system and going from Cartesian to spherical, just using some geometrical considerations. And if you go through this coordinate transformation for the coordinates and derivatives, what you'll find is the following. Lz is h bar over I dd phi, so it looks very similar to the case for the linear momentum. Just z is replaced by phi. And one can ask, with this operator, what are the corresponding eigenfunctions and eigenvalues? In order to try to figure this out, let's consider LZ acting on phi and its operator eigenvalue relationship. Now the question is, how do we solve this differential equation? Well, it looks sort of similar to what we did before, and it can look exactly like what we did before if we do the following. Just have the derivative acting twice. The operator acting twice, I mean. If we do that, we get the following expression. That's d phi equals minus m squared phi, which yields solutions we mentioned it's EDI something, and the coefficient is going to be m, and the variable is phi. Therefore, our operator eigenvalue relationship becomes this LZ squared phi is equal to m squared h bar squared phi. Okay. Therefore, LZ phi must be m h bar phi. Okay, and we know that the eigenfunctions for L squared should be eigenfunctions for L because they commute. That is LZ and LZ squared commute. Okay. And here m can take on values of 0, plus or minus 1, plus or minus 2, and so on. Now let's take a look at the eigenfunctions. If you recall, these are the spherical harmonics. That's L squared y equals L plus 1 h bar squared y of theta and phi. And this is pretty much just a given for this class, and later on you can play with deriving it. Okay. Where L squared has components L sub x squared plus L sub y squared plus L sub z squared. And L squared is equal to minus h bar squared 1 over sine theta, theta d theta sine theta d theta plus 1 over sine squared theta d squared d phi squared. Notice that there is some dependence on phi, and it's not only dependent on theta. And that's an important expression, so we'll put a box around it. And also note that L squared is the square of the total angular momentum. Recall that it has eigenvalues y in spherical harmonics, and eigenfunctions y and eigenvalues L times L plus 1 h bar squared. And note also that the angular momentum operator without the square has eigenvalues L times L plus 1 square root h bar. Okay. So let's recap. L squared acting on spherical harmonics has eigenvalues L times L plus 1 h bar squared, and L z acting on the spherical harmonics has eigenvalues m h bar times y. And as you might guess, if you consider the commutation relation between L squared and Lz is equal to 0, because they commute. And recall that spherical harmonics is product of this capital theta, these Laguerre polynomials, and capital phi. Now let's take a moment to do in class 2. And when you return, let's consider the commutation relations for Lx and Ly. I'll tell you what those are, and these are very important, so I'll put a box around it in the end. Lx does not commute with Ly. And the commutation relation yields IH bar LZ, which is at first glance rather curious. Okay. And let's make a comparison with what's familiar with the linear operators, x p hat equals I h bar. There is some similarity there. And notice that this Ly Lx also has uncertainty interpretation. And next up, we'll actually do another in-class assignment. So let's move on to in-class number 3. To enjoy doing some more problems. Okay. And next up, after you've taken a look at in-class 3, let's do some more in-depth studies of these commutation relations. Let's compare Ly, Lx, and Lz commutation relations with those of the linear operators, linear momentum operators, and x and y and z. The first one, let's look at x hat, p x operator, px operator. That's IH bar. Y py is IH bar, and so on. And these do not commute. As you know. And let's take a look at some other commutation relations, like the commutation relation of x and y. That's xy minus yx. That's just equal to 0 because they're interchangeable. Let's make another step. Okay, and x and py is equal to x h bar over I dy minus h bar over I dy x, and that's equal to 0 as well. We say that these are commuting operators. Now we can compare these linear operators, that is operators for linear momentum and x, y, z, with the angular case. Recall I told you that Lx commutes with does not commute with Ly to yield minus IH bar Lz. And it turns out that if you look at some other commutation relations, you find that none of these angular momentum operators commute. We'll focus on this one. And if you think about why that could be, intuition is if you rotate some object along one axis and rotate it along the other axis, you'll get the object, in some position in space. But if you reverse the operations of rotation, you won't get the same thing. So this is at the heart of why these angular momentum operators don't commute. And before we close for today, we have one last in-class assignment to take a look at. And when you finish taking a look at that, you'll be finished with class. Hopefully everything was clear. If not, please prepare some questions for the class discussion. Have a nice day.